I'm on a roll, so let's get going with what is hopefully my last video on this series for concave mirrors. This example is worded a bit differently, but I want you to see it. An inverted image is magnified by 2 when the object is placed 22 centimeters in front of a concave mirror. They want us to determine the image distance and the focal length of the mirror. So if you look back to these two equations, which one are we probably going to use? We're going to use the mirror equation or the magnification equation. Well, it tells us the inverted image is magnified by 2. They give us a value for m, and in the last video or some video I said that you are going to use any and or all parts of this equation, which means you can use all of it, you can use some of it. We're going to choose to actually include this m. Okay, normally I told you to cross it out because they didn't give us the magnification, but since they tell us it's 2, we have to include it. Now, in order for us to have an equation, we have to have two sides. The left and the right side. So are we going to include h for height or d for distance? Well, the only other piece of information we know is that the object is placed 22 centimeters in front of something. So we're given a distance. So we probably shouldn't use anything that deals with height. So I'm going to bring this equation down and we're going to work with it. So m is equal to negative di over do. We know the magnification is 2. We don't know the image distance, but we know that the object distance is 22 centimeters. Now, I would solve for the image distance, but I want to make one more thing clear. Technically, in the problem, it says that the image is inverted, which means it is the other way. So if I have a concave mirror right here, my principal axis, it is going in the other direction, which means technically, whatever this number is, whatever we get for di, it is technically a negative di. It's technically a negative di, which is something that's very, very unusual. Okay, so basically what we're saying is di is some number, and if it's some number, then it's upright. If di is a negative number, it's inverted. If di is a negative number, then negative di is equal to a number, okay, by multiplying both sides by a negative. Okay, well, another way of phrasing that is if your image distance is inverted, it's negative, which means not only do you include this negative sign that's automatically out front with the equation, but you also have to make sure that you are taking the negative image distance, which means that the negatives are going to cancel out and you're going to be left with a positive image distance over 22. And when you multiply both sides by 22, 22 times 2 is 44, and you get that 44 centimeters is the image distance. I know that was a little weird, but that's how you do it. As for the second part, so I'm going to go and denote that the image distance was 44 centimeters. It's asking for the focal length of the mirror, which is something that we haven't really ever been asked. So we used the first equation, and we used a different part of it first. Now we're going to use the equation we normally use first, and that is the mirror equation, because it's the only one with focal length. Okay, so let's see if we can fill this out kind of from memory. 1 over f, which we don't know, is equal to 1 over the object distance. Well, we know the object distance is 22, and we know that the image distance is a positive 44. So if you do the math, find a common denominator, you get that 1 over f is 44 over 3. Or, I'm sorry, 3 over 44. I'm ahead of myself. 3 over 44. Because the common denominator would be 44. Which means f, your focal length, is 44 thirds. That is an exact answer. If you want to be approximate, I think it's like 14.3. No, that'd be 42 and 2/3. So I don't know what I'm thinking. I just forget what I'm thinking. It's 14.7 centimeters. If you want to be approximate, but that's your exact answer. All right, heading over to the other problem I want us to look at. All right, a concave mirror forms an image on a wall 3 meters from the mirror. Okay, so let me go and denote that. Try to do this principal axis. Okay, forms an image on a wall. This is the wall. 3 meters from the mirror. Well, I'm given units in meters and I'm given units in centimeters and millimeters. I just like to convert everything to one thing and be consistent. So 3 meters we know is 300 centimeters. So this distance is 300 centimeters. The filament of a headlight lamp is 10 centimeters in front of the mirror. So about 10 centimeters in front, we have a lamp. That lamp has light in all directions. And this distance is about 10 centimeters. Part A. What are the radius and curvature and focal length of the mirror? The radius of curvature is just the center, or whatever your focal length is, times 2. Right? So if we know the object distance and we know the image distance, we can actually probably just find the focal length. Because we know 1 over the focal length is 1 over the object distance, which is 10, plus 1 over the image distance, which we know is 300. So I actually didn't do this one in advance, so I know that's going to be 1 over f is going to be, that's 31 over 300. F is going to be 300 over 31. That would be the focal length. So that would be this distance. That's the focal length. If they want the radius, then very simply, you can just multiply that by 2. Because the center of curvature is 2 focal lengths away from the center of the mirror. So I don't know if this is as a decimal. I guess I can probably find that out. Like 9.67, which I'll round to 9.68. .68 centimeters for our focal length, and the center of curvature, or the radius of curvature, would be twice that. So 2 times that, which would get us about 19.4 centimeters. Part B, what is the height of the image if the height of the object is 5 millimeters? Okay, so I'm going to denote that the focal length we got about 9.68, and the radius was about 19.4, just so I don't lose that. And then we're going to go and use the other equation, the magnification equation. It doesn't give us m, so we're not going to use that portion of the equation. Instead, we're just going to use hi-ho and negative dido. If this will ever erase. Come on. I might have to redo this video. Oh, this is slow for no reason. All right. Hi-ho. Negative dido. What's the image height? Well, we don't know. What's the object height? Well, it says the height of the object is 5 millimeters, which we're going to have to convert to centimeters. That's 0.5 centimeters. Negative, and then the image distance. Well, the image distance is 300 centimeters, and we're doing everything in centimeters. And the object distance right here is 10 centimeters. So I'm going to multiply both sides by 0.5, and I get that HI is negative 30 times 0.5, or simply negative 15 centimeters. Let me just double check that that's right before moving on. Yeah, that looks about right. All right, so the last part of this video I want to devote to talking about a really cool term called spherical aberration. I'm a word nerd. If you want something to do in your free time, Google the word aberration and it's going to come up with a plethora of synonyms and you can just have fun with that. All right, spherical aberration. Now, in the beginning, in the first video, the introduction to a curved mirror, I postulated that if you have some sort of a sphere and you cut it in half, and you coat the insides with something like silver, and you would get a concave mirror system. And I said that the terms spherical and parabolic are not synonymous, meaning you can't just interchange them whenever you want. They're not identical terms, but they are similar. They're both dealing with concave mirror systems. Well, I'm going to talk about the differences right now to close this off. If you have a spherical mirror, there is some sort of error. Okay, normally with a concave mirror, we understand the two principles of drawing a ray diagram, and that is, number one, if you're parallel, you go through the focus. Number two, you go through the focus, you're parallel. And they meet, and you draw a ray diagram from that. So all these rays are coming together at some sort of a focus. In a spherical mirror, this actually doesn't happen. All the rays, all these incident rays are coming in and they're slightly off. So you might have a ray coming in here, and a ray coming in here, kind of close, and here, and here, and they're not all meeting in the exact same location. Okay, they're kind of spread out, which in turn is going to make wherever your image is slightly blurry if you use a perfectly circular mirror. If you use a parabolic mirror, the image is going to be finer, you're going to see a higher resolution, and that's because everyone meets at the focus. Okay, and if you want to know the difference between a sphere and a parabolic mirror, basically here it is. A spherical mirror is going to derive itself from a circle. Okay, so if I cut a part of that circle, kind of get this. A parabola or a parabolic mirror comes from a parabola, which is more curved. Okay, so this one, the parabolic mirror, is going to produce images that are higher in resolution, and the spherical mirror is going to make the image slightly blurry. This is called spherical aberration. Aberration is just another word for like error or kind of mistake, and the error is that all these rays aren't coming together at the same point. So just in case you ever see that term aberration, that's what it means. Thank you for being extremely attentive through my videos and lectures through concave mirrors, and I hope to see you in the next section or next set of videos where I discuss convex mirror systems.